Welcome my dear students to the part 2 of today's session. In this module, let us discuss about the stress-strain curve, elastic moduli, Young's modulus and bulk modulus. Let us first see the stress-strain curve. A graph is plotted between stress and strain, taking strain along the x-axis and stress along the y-axis. The shape of the graph is as shown by the blue curve. You can see the regions OA, AB, BC, CD and DE on the curve. In the region between O to A, the curve is linear. In this region, Hooke's law is obeyed. So you can refer to the region OA, where stress is proportional to strain or the Hooke's law is obeyed. In the region from A to B, stress and strain are not proportional, but the body returns to its original dimension when the load is removed. The point B in the curve is known as yield point. It is also known as elastic limit. And the corresponding stress is known as yield strength of the material. So you can see that in the section from A to B, the object returns to its original dimension after the removal of the applied force. The point B is known as elastic limit or yield point. If the load is increased further, that is the curve between B and D, the stress developed exceeds the yield strength and strain increases rapidly even for a small change in the stress. When the load is removed, say at some point C, between B and D, the body does not regain its original dimension. In this case, even when the stress is 0, the strain is not 0. The material is then said to have a permanent set. The deformation is said to be plastic deformation. The point D on the graph is the ultimate tensile strength of the material. So you can see in the region between B and D, if the force is removed, the object will not return back to its original dimension, but it will have a permanent set. And in this region, it shows its plastic behavior. Beyond this point, additional strain is produced even by a reduced applied force and fracture occurs at the point E. If the ultimate strength and fracture points, that is D and E, are close, then the material is said to be brittle. If they are far apart, the material is said to be ductile. So you can see after this region D, even though if you are applying a lesser amount of load or stress, more strain is produced and it can fracture at any point. Suppose if it is getting fractured at the point E, then point E is known as the fracture point. If the distance between D and E is little, then we can say the substance is brittle. If the distance between D and E is large, the object is said to be ductile. The stress-strain curves vary from material to material. This stress-strain curve is drawn for a metal. And these curves help us to understand how a given material deforms with increasing loads. So we have seen in the region OA, Hooke's law is obeyed. In the region between A and C, A and B, Hooke's law is not obeyed, yet the object returns to its original dimension. In between B and C or B and D, the object is said to have attained a permanent set. After D, fracture can occur at any point, and the point at which fracture occurs is called the fracture point. Now, let us discuss about Young's modulus. For a solid in the form of a wire or a thin rod, Young's modulus of elasticity within elastic limit is defined as the ratio of longitudinal stress to the longitudinal strain. It is given as Young's modulus capital Y is equivalent to F by A divided by delta L by L, or it is equivalent to F into L divided by A into delta L. F can be replaced by mg into L divided by area can be replaced by pi r square into delta L. It has a unit of longitudinal stress, and the dimension of Young's modulus is ml raised to minus 1 t raised to minus 2. Its unit is Pascal or Newton per meter square. Now, let us discuss about the bulk modulus. Within elastic limit, the bulk modulus is defined as the ratio of longitudinal stress to the volume strain. It is given as bulk modulus B is equivalent to F by A divided by delta V by V, which is equivalent to minus P divided by delta V by V. Here, force per unit area is replaced by pressure P. The negative sign in the bulk modulus indicates that the volume variation and pressure variation always negate each other. The reciprocal of bulk modulus is commonly referred to as the compressibility. It is defined as the fractional change in volume per unit change in pressure. This is the table for Young's moduli, elastic limit and tensile strengths of some materials. You can see that the Young's modulus for steel is much greater compared to other materials. This is the table for bulk moduli of some common materials. From this, it is clear that solids are having a higher value of bulk modulus compared to liquids and gases. And among the solids, nickel shows a greater value for bulk moduli. This is a table which defines stress, strain and various elastic moduli for materials. In this, the tensile or compressive stress, the corresponding strain, elastic moduli, name of the elastic moduli and state of matter of the material is shown to you. Similarly, for shearing strain, the respective data of stress, strain, change in shape or volume, elastic modulus, name of the modulus and state of matter is shown. The same is shown for hydraulic stress too. Hope you have got an idea about the stress strain graph and also the various types of moduli of elasticity. Thank you, dear students.